Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to today's lecture on advanced transition metal organometallic chemistry. Today we are going to be continuing with our topic of transition metal cyclopentadiene complexes, their preparation and properties. Now, these metal cyclopentadiene complexes are of historical importance, particularly with the development of organometallic chemistry or development of the field of organometallic chemistry, and from that perspective these transition metal cyclopentadienyl complexes that we are discussing over the last two lectures assumes relevance. In our earlier lecture we had seen how this ferrocene, the so called representative of transition metal organometallic complexes, was first synthesized independently by two groups in 1951, followed by their structure resolution coming in 1952 by Fischer, and which at that point of time answered a big question about as to how two cyclopentadiene ligands are binding to the transition metal, and these would be interactions of aromatic pi type orbitals with the metal, which will hold these metallocene or ferrocene complexes containing transition metal cyclopentadienyl bonds. At that point it was a huge discovery in terms of ligand metal interactions are concerned. And then we have also looked at various ways of preparations that people adopted for preparing these transition metal cyclopentadienyl complexes. Some of them include simple salt metathesis reactions with Cp anions exchanging with metal halide precursors or other kind of metal salts. Also reactions with of Grignard were chosen for a source of Cp anions for metallating it on other metals. And then continuing further on these various synthetic routes that are available for preparing this metallocene or transition metal Cp complexes, we are going to look at few more preparations which are available in today's lecture to begin with. Similarly, along the same line one can see that reaction of metal salt with cyclopentadienyl for in case of copper, for example with triethyl phosphine copper t-butoxide and cyclopentadiene gives eta 5 H5 Cu Et3P along with t-butanol. So, over here this t-butoxide moiety on copper is getting protonated with Cp hydrogen. Now, the driving force for this protonation arises from the fact that after protonation the Cp anion being generated is resonance stabilized because of the attainment of aromaticity, and that probably drives this reaction forward to producing the Cp eta 5 bound Cp copper triethyl phosphine derivative. There are reports of such deprotonation affected by using base. For example, there are general reports of using metal salts and cyclopentadiene in presence of base doing the same thing. For example, thallium sulphate plus 2 C5H5 plus 2 OH minus is an external base resulting in water gives this C5H5 thallium plus water plus sulphate anion. Similarly, reaction of FeCl2 plus 2 C5H6 plus 2 diethylamine giving ferrocene plus 2 NH2Cl. So, the take home message is, if the basicity of salt anion is insufficient to deprotonate cyclopentadiene, then a base is required, and this is illustrated by comparing these two reactions. No base was used in the reaction with the copper t-butoxide, as this t-butoxide anion, the basicity of t-butoxide anion could easily deprotonate cyclopentadiene proton, dienyl proton, whereas the anions like sulphate or chloride in these examples are not basic enough to deprotonate the cyclopentadienyl proton, and as a result some ancillary base, in the thallium sulphate case it was hydroxide, and in the iron chloride case it is diethylamine, was required to produce the cyclopentadienyl anion bound to the transition metal. In some cases also the presence of reducing agent is required. So, the strategy is similar to what we had seen earlier, but that now instead of base a reducing agent is required. For example, in this strategy it involves metal salts plus cyclopentadiene plus reducing agent, and the reaction is given as three C5H6 in presence of reducing agent like zinc in ethanol gives ruthenium plus H8 zinc plus. So, in some cases reducing agent is necessary, and here is an example where zinc was used as a reducing agent for carrying out this reaction. Now, in order to understand the reactivity or bonding in metal cyclopentadienyl complexes, one needs to take a look at its molecular orbital. Now, we have been doing this treatment particularly to understand the reactivity as well as bonding interaction in various metal ligand that we have discussed so far. We have started with allele, then which is a C3 system, to butadiene C4 system, again cyclobutadiene C4 system, and now we go on to try and look at the metal ligand interaction in cyclopentadienyl system. Now, as we go up in the number of carbon atoms, so this is a 5 membered ring, and hence we will have 5 p orbitals. So, the complexity of these interactions also increases tremendously, and to the extent possible I am going to explain this with the help of diagrams which will simplify these interactions to the reader. So, let us take a look at structure and bonding of the cyclopentadienyl ligand with respect to the transition metal orbitals, and to start with we look at their MO orbital properties. So, cyclopentadienyl ligand will have 5 p orbitals resulting in 5 molecular orbitals, of which there will be one of its own type and the 2 other will be degenerate. So, they are shown over here. So, this is psi 1, which is A1 symmetry, and this is all bonding. So, now there are 2 E2 types. And another So, this one has one nodal plane and this one has another nodal plane. These two are degenerate and is referred to as E1 symmetry. Now, this has two nodal planes, one between this and another between this, and the fifth combination is that one also has two nodal planes, and these two are also degenerate and are called E2 types. So, these orbitals, so what we see that the 5 p orbitals, they mutually combine in different ways to generate 5 fragment molecular orbitals, of which one is non degenerate and 2 pairs of degenerate orbitals E1 and E2. So, orbitals are paired to form symmetry adapted linear combinations or SALC, which overlap with metal orbitals with of appropriate symmetry. So, now the bonding scenario that is presented will get even complicated further, because of the fact that in ferrosinyl complexes there are two such CP ligands, and depending on the orientation of each of the fragment orbitals, they would interact differently with the metal orbitals. And this I will illustrate with a set of orbitals which is CP. So, there are two CP rings and these two rings are opposite, facing opposite of each other. So, one is pointing this, the other is pointing it, and So, these two orbitals of the ligand interacts with a metal orbital which is dxy. This is the metal orbital, and such interaction is called a delta type interaction, and this combination of ligand orbital is called E2G ligand. Similarly, the other metal orbital for the E2G group would be like and the corresponding the other Cp So, this also is a E2G ligand orbital, and the metal orbital corresponding to that dx square minus y square, and this interaction is also a delta interaction. So, what we see is that delta interaction is a weak interaction and also is less favored and it involves a dative bond between Cp E2 ligand from iron dx y or d x square minus y square orbitals. So, this is a metal to ligand delta back donation, and hence this is a weak interaction. Let me just go a step further and bring back the earlier slide, and what we see that 5 sets of orbitals to E1, E2 and A1 type is formed from one Cp, and when both of the Cp comes, then we have 2 combinations because each of the ring appears top and the bottom, and what we see that the E2 portion, the top most degenerate orbital, these two are responsible for the delta interaction which happens from metal to ligand. Metal to ligand interaction happens over here, and A1 and E1 are the filled cyclopentadienyl anion ligand, and ligand to metal, the opposite interaction, ligand to metal interaction would happen over A1 and E2. So, today we have looked into various types of preparative methods that are out there for preparing this transition metal cyclopentadienyl complexes. In addition, we have also looked at the structure and bonding, particularly from the molecular orbital perspective of these transition metal ferrocinyl complexes, particularly how the p orbitals of the ferrocene cyclopentadienyl ligand rearranges themselves, orient themselves, so that they become ready for interaction with the metal, and how they interact based on their energies. So, with this I will conclude today's lecture, and we are going to look into this bonding aspect of cyclopentadienyl ligand with the metal orbital in much more detail in subsequent lecture, where we are going to build this CP metal interaction along the same lines in much more detail, looking into ligand to metal sigma and pi interaction. Today we have built the molecular orbital correlation, the picture, and also had looked into metal to ligand delta interaction, which is obviously very weak and also does not happen in many instances. So, with this I conclude today's lecture, and we are going to be taking up this structure and bonding of transition metal cyclopentadienyl complexes is much more detailed in the subsequent lecture. Till then, thank you and goodbye.